Hello students, welcome to AIMS India online classes. This is a chemistry session. Here we are going to discuss about the chapter periodic classification. In the earlier sessions, we have seen how this modern periodic table is constructed, on which basis it is constructed, and what are the different special names given for the groups and periods. And we have started the learning about trending of atomic properties in the groups and periods of the modern periodic table. Already have seen about atomic size variation. Now in this session we are going to say about ionization energy and its trending in the groups and periods. Okay, what is ionization energy? Ionization energy of an element can be defined as the minimum amount of energy required to remove the outermost electron from an isolated neutral gaseous atom is known as ionization energy. What is the definition given for ionization energy? The minimum amount of energy required to remove an electron from the isolated gaseous neutral atom to make it unipositive ion is called ionization energy or ionization potential. For example, it is an atom. Suppose certain energy is given to an atom. Then the atom may lose an electron from its outermost orbital. There, the amount of energy required by that atom to remove this electron from its outermost orbital to exit this electron from its outermost orbital, the amount of energy required by that atom is known as ionization energy. But before that, atom should be isolated from the remaining all atoms, because single atoms, they won't exist generally. They might be in the molecular form or in the compound form. So first, that atom should be isolated. In that isolated neutral state, there, the amount of energy required by that atom to eject an electron from its outermost orbital, the energy required is called ionization energy or ionization potential. Okay, so it can be expressed like this equationally. Suppose an element X is taken isolated gaseous form, atomic form it is taken. So from that atom, the minimum amount of energy required to remove an electron from its outermost orbital is known as ionization potential. So if ionization potential is given to a neutral gaseous atom, then by taking this energy, that atom will eject an electron and forms a positive ion. There, the amount of energy required by that atom to eject this electron is called ionization potential. Okay, as we're telling, this is a energy. Then units of this ionization potential will be electron volts, kilojoules, kilocalories. These all will be the units of this ionization energy. But in terms of a certain quantity, if it is taken, then it can be expressed as electron volts per atom, kilojoules per mole, kilocalories per mole. So these will be the units of ionization potential. So the minimum amount of energy required to remove an electron from the gaseous atom is called its first ionization potential, because from certain elements more than one electron also can be removed. Yes, there are some metallic elements which can lose more than one electrons in the compound's formation, isn't it? So out of this, there the amount of energy required by those atoms for the removal of first electron is called first ionization potential. It can be defined like this. The minimum amount of energy required to remove an electron from a gaseous atom, gaseous neutral atom, is called its first ionization potential. Then the second ionization potential is the energy required to remove an electron from the outermost shell of an unipositively charged gaseous ion. Means from the neutral gaseous atom, if one electron is removed, it will be converted into unipositive ion. There the amount of energy required by that atom for removal of that first electron is called first ionization energy. So after that, it becomes an uni-positive ion. Now, if you want to remove second electron from that, there the amount of energy required for the removal of an electron from that uni-positive gaseous atom is called second ionization potential. And then if you remove third electron, that is defined as the minimum amount of energy required to remove an electron from the isolated dipositive gaseous atom or gaseous ion is called third ionization potential, and so on. Got it? So it can be expressed like the second ionization potential. So already that neutral atom is converted into uni-positive ion by the removal of an electron. This is that X plus means it is representing an uni-positive ion. From further, if certain amount of energy is supplied, then it will lose one more electron and forms dipositive ion. There the amount of energy required by the uni-positive ion for the removal of second electron is called second ionization potential or second ionization energy. Okay. For example, if you see sodium, actually it is a sodium solid metallic substance. First, that sodium atom should be isolated from the remaining sodium atoms, and then it should be converted into gaseous state. In that gaseous isolated state, for the sodium atom, if this much amount of energy is given for 1 mole of atoms, then they release all atoms 1 electron from each. So the first ionization potential for sodium we can say as 495.8 kilojoules per mole. Means if you take 1 mole of sodium atoms in the gaseous state, then for those if we supply 495.8 kilojoules of energy, they release 1 electron from each from their outermost shell and they form uni-positive ions. That energy supplied is called here first ionization potential. Now what happened? By supplying this first ionization potential, sodium atoms became sodium ions or uni-positive ions. So if you want to remove an electron from these positive ions, then we need to supply some more amount of energy. So there the amount of energy supplied for the removal of second electron from an uni-positive ion is called IP2, that is ionization potential 2, or we also can say second ionization potential. Okay. Next, similarly, we can define third and fourth ionization energies or ionization potentials for these atoms. Okay, as we discussed here, first and second, the remaining also you can say in the same way. The amount of energy required to remove the third electron from a neutral atom means the amount of energy required to remove an electron from the dipositive gaseous atom, the gaseous ion, is called third ionization potential. In the same way, the amount of energy required to remove an electron from the tripositive gaseous ion is called fourth ionization potential. In this way, we can define them. If the first ionization energy is considered as IP1 and the second as IP2 and third as IP3 and so on, then always for any atom, IP1 will be less than that of IP2, that is less than that of IP3 and so on. Means the amount of energy required to remove first electron from an atom will be always lower than the amount of energy required to remove second electron from the same unipositive ion, and it will be less than that of the second one. In that way it will be related. So theoretically an atom can have as many ionization potentials as there are electrons in it, but theoretically it will be possible, but practically it may not be possible. We can define this theoretically as how many electrons are there, those many ionization potentials will be possible for an atom, but practically all the electrons cannot be removed, of course. Okay. For example, first, second, third and fourth ionization energies of magnesium and aluminum are mentioned here. See, if you see any atom, always the first ionization energy will be lower for that, and the second ionization energy will be greater than the first one, and third will be greater than that of second. In that way, they are in the increasing order. Why it is so? Do you know? Because if you see aluminum itself, We know it has 13 electrons, isn't it? Because its atomic number is 13. And in the nucleus, it will be having 13 protons also. Now, if you supply this much amount of energy in terms of kilojoules per mole, then aluminium loses one electron and forms Al plus. Then what happens? Here it will be having only 12 electrons, whereas number of protons is being same, but number of electrons is reduced to 12, isn't it? By the removal of one electron. Now, as nuclear charge is more, the remaining 12 electrons will be held by the nucleus strongly. So, the removal of one more electron further requires more and more energy. That's why here if you observe, than the first ionization energy, second ionization energy is greater. So if you supply this amount, then second electron will be removed from the aluminium and it will be converted into Al plus 2. So then how many electrons will be in this now? Only 11 electrons. But the nuclear charge is remained still at 13 protons. Now the nuclear charge is much increased. Means it is 13 only, but number of electrons is reduced. Positive charge is much greater than negative charge. So the remaining electrons will be held by the nucleus much stronger. So the removal of one more electron further becomes much more difficult. So for the removal of third electron, this much amount of energy is to be supplied. So it is much greater than the second one, isn't it? Now if you supply this amount, then aluminium atoms lose a third electron and they convert into Al plus 3 ions. Now the number of protons is being 13, but number of electrons became 10. Now much greater nuclear charge is there, so the remaining electrons will be held very tightly by the nucleus. The removal of further electrons becomes much more difficult. Okay, in this way, always for any element, first ionization energy will be less than that of second ionization energy, second will be lower than that of third, and so on. Got it? Next, this successive increase in the values of ionization potential is due to the increase in the effective nuclear charge from the neutral atom to respective ions. This is the main reason as being increased. Okay. Variation of ionization energy. So now we have seen what is meant by ionization energy. Now we are going to see how this ionization energy varies in the groups and periods of the modern periodic table. So ionization energy shows periodicity, means it will be changed from one element to element and it will be repeated. That means it varies in a respective way as you move through the periodic table in the left to right in a period or from top to bottom in a group. Now we are going to see here how it is varying in the groups and periods of the modern periodic table. First let us see in a period. In general, the ionization energy increases across a period. So, as we move from left to right of the modern periodic table, ionization energy generally increases. Because as we move from left to right in a period, size of the atoms decreases and nuclear force of attraction increases. Hence, it requires more energy for the removal of an electron from the atoms and ionization energy increases. Okay, as we told in the earlier class about the atomic size, in a period from left to right, atomic size decreases. At the same time, nuclear charge increases. So what happens? The electrons in the valence shell will be bound strongly. The removal of electrons becomes difficult as size decreases. So in a period from left to right, generally ionization energy increases. Okay. The noble gases are usually associated with the highest ionization energy. Yes, because these elements are having completely filled outermost shell and they are stabilized. They will require much more energy to disrupt the stability. We know these noble gases which are at the extreme right side of the periodic table, they are having completely filled outermost shell, that we say octet or duplet configuration, isn't it? So because of this, the removal of electron from these elements becomes very difficult because high and high amount of energy should be supplied to disrupt this where octet configuration or duplet configuration. Hence, their ionization energies are highest in a period. Okay. On the other hand, the group 1 elements are usually associated with the lowest ionization energy. Yes, we told in a period from left to right, ionization energy increases because size of the elements decreasing from one to another. And hence, the elements which are at the extreme right side are having greater ionization potential. What are those elements at the extreme right side? They are noble gases. Not only the size, there one more factor affecting their ionization energy, that is their stability, their octet configuration. Because of these two, they are having the highest ionization energy in a period. Whereas if you see the extreme right side, left side elements, they are alkali metals or first A group elements. They are the elements which are having greater size in a period. Okay. Now, as they are having the greater size, the nuclear distance to the outermost orbital will be greater, and hence the removal of electron becomes very easy from those atoms. What we can say, by the supply of limited minimum amount of energy only, they release electrons. So thus we can say these elements which are at the extreme left side of the periodic table, they are alkali metals. They are having least ionization potentials in a period. So if you take any period in the periodic table, alkali metal with the least ionization energy and noble gas is with the highest ionization energy in that period. For example, if you take third period from sodium to argon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. Out of these all elements, sodium is the extreme left side element, that is alkali metal. So it will be having the greatest size among these all, and hence it is the element with the lowest ionization potential among these. And the element at the extreme right side is argon. So argon is the element with the highest ionization energy in that period. Okay. For example, look at the pattern from, okay, one more example they are mentioning here, that is lithium to neon and sodium to argon. They have mentioned their ionization energies variation chart in the graphical way. Bar graph they have given. See, first from hydrogen if you see, it increased to helium. In the first period, it is gradually increased. And from lithium to neon, of course, there are some slight changes, but gradually it is increased generally we can say. From lithium to neon, gradually ionization energy increased. But there are some exceptions which we are going to learn in the further classes. But generally we can say it is increased from lithium to neon. Isn't it? And if you see third period elements, from sodium to argon, here also there is gradual increase. Okay, so from this what we can say, in a period in general from left to right, ionization potential increases because size of the atoms decreasing. Okay, next, what happens in a group? The ionization energy decreases from top to bottom in a group. This is because as we go from top to bottom, the size increases and attractive power of the nucleus on the outermost electrons decreases. Therefore, it is easy to remove the electron and hence ionization potential will be decreased. If you see for certain elements, the elements present in the first group, for them the ionization energies are mentioned here. See, gradually they are decreased from lithium to cesium. So lithium is having the highest ionization potential among these all, and then sodium, and then potassium, rubidium, cesium, francium. So what is happening here, from lithium to potassium, francium or cesium in that group, if we observe, size increases. Lithium has only 2 shells, whereas sodium has 3, potassium has 4, and the number of shells gradually increasing from top to bottom in that group. As number of shells increasing, what happens? Size also obviously increases. If size increases, the distance from the nucleus to the outermost electron increases, and hence attractive power on this outer electron by the nucleus will be less. So what happens now? By the supply of minimum amount of energy only, that electron will be ejected out. That we say as less amount of ionization energy. So as the size increases, ionization energy decreases. So in a group size increases, and hence we say from top to bottom in a group ionization potential decreases. Got it? So here we say from these two summarizations, helium is the element with the highest ionization energy. Yes, we can say this because we are telling in a period from left to right, ionization energy increases, isn't it? In a period as you move from left to right, ionization energy of the elements increases. So what is the element at the extreme right side of the period? Noble gas. So noble gas will be having the highest ionization energy in any period. Now in a group, if you say in a group from top to bottom, ionization energy decreases because size increasing. Now the topmost element will be having the greater ionization energy. So extreme right side topmost element is having the greatest ionization energy among all the elements. So the extreme right side topmost element is helium, isn't it? At the extreme right side, the first element at the top is helium. It is having the smallest size and completely filled on configuration, and hence it is the element with the highest ionization potential. Okay. Let us see some solved examples based upon this variation of ionization potential in the modern periodic table. See the first question. From their locations in the periodic table, predict the correct order of first ionization energies of these elements. What are those? Fluorine, iodine, bromine and chlorine. Did you find any relation between these elements? Yes, there is a relation. What is that? These all elements belong to same group. Now let us see the answer. These four elements are present in the same group, that is 7th A group. We know these elements are halogens, isn't it? So top to bottom if you say, they will be in the order fluorine, chlorine, bromine and iodine from top to bottom. So as we know, ionization energy in a group from top to bottom, it decreases because size increases. So we can show the correct increasing order. What they're asking, either decreasing order or increasing order. Correct order they mentioned. So we can mention any order here in this way. Fluorine has the greatest and next to chlorine and then bromine and least for iodine. Because from fluorine to iodine, size increases. As size increases, nuclear force of attraction on the outermost electron decreases and hence ionization energy decreases. Got it? Let us see one more solved example on this. Use their locations in the periodic table to predict the which element has the lowest first ionization energy among these elements. Here they mentioned certain elements. Now we have to identify among these which element is having the lowest ionization energy. That can be identified if we are able to positionize these elements in the periodic table. If you understand the positions of these, let us see solution. These six elements form a rectangle in the two far left column of the periodic table like this. Yes, of course, these all elements belong to alkali metals and alkaline earth metals, isn't it? Potassium, sodium belongs to, and even rubidium also belong to first A group alkali metals. And next calcium, magnesium and strontium. These three elements belongs to alkaline earth metals. If you positionize these in the periodic table, they form a rectangle like this. Now the point is, as we know, the ionization energy increases from left to right. So in this way, from left to right in the periods, ionization energy increases. Now, so if you see from left to right like this, which elements are having the lowest? They're asking about lowest first energy, no? So these first group elements are having the lowest ionization energy. Out of these three elements also again, these three are in the same group, isn't it? Now, Out of these all, the element which is at the bottom will be having lowest, because in a group again the ionization energy decreases from top to bottom because size increases. So out of these all, which will be having the greatest size, that is rubidium. Rubidium is the element with the lowest ionization potential among these six elements. Got it? In this way, we can derive the relation between the elements, and hence we can find out which is having greater or lowest ionization potential. Okay. Thank you for watching our video. Please subscribe our YouTube channel Aims Today for latest updates and recorded videos.